Hello and welcome to the MOOC on optical communications. In this module we will look at some effects of amplified spontaneous emission noise in an optical amplifier, and in ultra long haul communication links what effects would this ASC noise or ASC induced noise would have on the performance of the system. We remember or we recall from earlier modules that an optical amplifier, that could be a semiconductor optical amplifier or it could be an erbium doped fiber amplifier, is characterized by two things. One, it is the gain of the amplifier, which means that if at the input terminals of the amplifier we have an input power of P in, optical power of P in, at the output terminals of the amplifier we get a power which is G times P in. As we said, optical amplifiers or any other amplifier for that matter are not going to be ideal amplifiers, in the sense that in addition to this signal there would also be a ASC noise, right. There would also be noise. In the context of optical amplifiers it is ASC noise, because that is primarily coming from the amplified spontaneous emission. So, spontaneous emission in the active medium of the optical amplifier, which then gets amplified and shows up as output amplified spontaneous emission noise, compared to the signal which is usually a narrow band signal because it is modulated at a particular modulation rate onto an optical carrier. The amplified spontaneous emission noise is wide band. Okay. Therefore, if you want to limit or if you want to work with the optical output that is coming out of the amplifier, you somehow have to also limit the amount of noise that is entering into the subsequent devices or subsequent components of the optical link. You do that by actually putting a output band pass filter. So, you actually have an output optical band pass filter in order to limit this amplified spontaneous emission noise only to the bandwidth that the signal occupies. Okay. So, all these components of the amplified spontaneous emission noise outside the bandwidth is all equal to 0. Well, we have looked at what happens. Actually you get this ASC not just as the ASC component, you also get, in addition to this, the signal and the ASC beating, which we called as the signal spontaneous. We also see that the spontaneous emission or the ASC itself will beat with the ASC, giving rise to spontaneous emission. Okay. In a usual operation, it is the signal spontaneous noise that is quite dominant compared to the spontaneous emission noise or the spontaneous beating of the optical amplifier. So, this is essentially what is actually happening with an optical amplifier and a band pass filter. The effect of the amplifier is to actually reduce the signal to noise ratio at the output, or rather worsen the signal to noise ratio, but this is not bad because without the amplifier you would not even be able to detect any signal. Okay. So, although the signal to noise ratio at the output seems to be decreasing or degrading, this is offset by actually looking at the gain in the signal actually increases. Okay. So, this particular characterization of an optical amplifier or any amplifier for that matter is characterized by the noise figure of the amplifier, and for the erbium doped fiber amplifier under reasonably best conditions we saw that the noise figure will be roughly 3 dB. Now, let us consider a slightly different problem. We consider what happens on a ultra long haul optical communication link. We will stick with on off keying for the moment. If you are wondering what on off keying is, probably it's just a bit too easy to refresh your mind. You have bits 1 and 0. So, when you want to transmit a bit 1, you transmit it by sending a pulse. When you want to transmit a bit 0, you transmit nothing, right. So, the optical power here will be P1, the optical power here will be equal to P0. Again, you can have the NRZ variety or the RZ variety. For our purposes it does not really matter which one is which, although we will consider the NRZ variety of the optical pulses in our discussion. Okay. So, at the transmitter you have the on off keyed pulses that are coming out, and then you have a fiber link through which this intensity modulated or on off key modulated signals are passing through, and after they have passed a certain length, which let us call it as LA, the level of the optical pulse would have reduced because of the attenuation in the fiber, which is what we are only considering. We are not going to consider the dispersion aspects. So, you start off with a pulse that would look like this. At the end of the length LA of the fiber, the pulse amplitude would have decreased. Okay. So, you started off with say some P in, the power that you get here will be P in e to the power minus alpha into LA, where alpha is the attenuation coefficient of the fiber, LA is the length of the fiber that you have connected. If this happens to be less than the sensitivity of the detector, right, then it would be not possible for us to realize that there is actually a pulse that has been transmitted. So what we do here is to actually pull up the amplitude by giving an appropriate value of the gain. Okay. So you actually have an amplifier with a gain, let us call this as G1. Okay. Then of course you still have one more fiber link. Let us for simplicity assume that the fiber link has the same length LA. Before you give in the amplifier of a gain G2, then you keep doing this until you come up to the last length, right. So here you actually have a length LA, and the amplifier that I am using will have a gain of Gn. We will see that all these gains are normally equal. Okay, you do not normally see the amplifier with different gains for various purposes, but before making that assumption, let us also put down the optical band pass filter, okay, and then look at the output. So this is the system that I want to consider. So whatever that comes out of the optical band pass filter can go into the receiver. So you can actually put a photodiode, or you can put a coherent receiver and then amplify the signal. But if in this system things seems to be very simple, actually things are not really simple. See, you start off with a certain power P in, okay, the average power that you start off here, let us say, is given by P in, and this is, let us for now assume that this is a continuous wave signal, that is P in bar, or the mean optical power, is actually going to be constant. Now due to the fiber there is an attenuation, okay, so the power actually reduces by a certain factor, but because you have put in a gain, the power actually comes back. Okay. If you call the loss factor here, which is e to the power minus alpha LA, as H1, okay, H1 denoting the loss in the first fiber link, G1 denoting the gain of the first amplifier that you are going to put in, okay, then you again the power reduces because there is a loss factor H2, because the optical signal is propagating in the second link as well, and from here you again pull the output back by supplying a gain of G2, and this process keeps on reducing until you come to the last stage where again there is a factor Hn, okay, because of the nth fiber span, and then you pull the amplitude back up to get the total gain of Gn, okay, and this would be filtered. Let us assume an ideal band pass filter, which means that it is not decreasing the amplitude of the signal. So this goes to the receiver side, okay. So the mean received power can be obtained by looking at the loss and the gain and then multiplying each of these components, right, because the power at this point is simply given by P in bar H1, while the power at this point is given by P in bar H1 G1, correct, and the power here is given by P in bar H1 G1, which is the power from the previous stage times the loss factor H2, and finally the power here will be given by the power at this stage, which is P in bar H1 G1 H2, and then pulled up by the gain G2, okay. And therefore if you come all the way up to the receiver side, you see that the power at the receiver should then be given by product of all this, right. So you actually have P in bar, which is the input power, times H1 G1 H2 G2 and so on all the way up to Hn Gn, right. So the loss factor and the gain factor are both getting multiplied with each other, okay, and in general one can always assume that H1 is different from G1, H2 is different from G2 and so on, but normally that is not what is done, because then the amplifier spacing becomes unequal, the saturation power of the amplifiers become different. So in order to avoid all these problems, you normally take all the amplifier losses to be the same, that is Hi is equal to the same value of H, which is given by e to the power minus alpha into La. This you can do by putting all the amplifiers at a equal distance from each other. So the spacing La, which is called as the amplifier spacing, is kept constant, and of course how many stages we have? We have I is equal to 1 to all the way up to n, okay. So you can write down what is the power that you are receiving in a shorthand way by introducing this symbol called as pi symbol and then write I is equal to 1 to n. It simply means that you have to take a product of the terms of the form hi gi. Okay. So, this is a shorthand notation to write down this particular factor. Okay. So, this is what you get at the receiver side, and we have already said that all the loss elements h will be the same. So, you can pull that h element because it does not depend on the index I outside of this case. So, you simply write down this as p in bar and then h. Of course, you are going to multiply this factor n times, correct. So, what will happen, although that is not dependent on I, it is actually what we mean is that this is actually constant and independent of the value of I, but this factor gets multiplied n times. So, what you get here is e to the power minus n alpha L A. Does this make sense? In a sense, yes, it does make sense, because you started off with the transmitter here and then you started placing an amplifier at each positions, right. So, you placed an amplifier, between there is a fiber, and so on we did until we ended up with the last amplifier. What is the total length from the transmitter to the receiver side here? It would be equal to L A into N. Does it make sense? Yes, because the amplifier lengths, okay, if you are using an erbium doped fiber, this amplifier length is about say 8 to 10 meters, whereas this LA is typically from anywhere between 60 to 125 kilometer, with frequently the values being at 100 or 80 kilometers. Okay. So, at 100 or 80 kilometers, that would be very, very large compared to this small 8 into 10 meter loss. Okay. So, you can either absorb the loss in this erbium doped fiber amplifier or the semiconductor optical amplifier back into this factor h and then work with it, or you can simply ignore the losses at this point, they are not going to be very large, and then realize that the distance from the transmitter to the second amplifier is about LA into 2, and after n amplifications the distance would be LA into n. Let us call this factor as total length. So, what we are saying over here is that the factor e to the power minus n alpha LA simply tells you what is the total fiber length. This fiber length is different from the amplifier fiber length or the amplifier length of a semiconductor optical amplifier if you were to use that one. Okay. And the total loss over that total length L total is given by e to the power minus n alpha into LA. Okay. This factor we have obtained. What about this factor Gi? Now, it is in principle, as I said, possible to actually have various values of this Gi. Okay. So, you can actually make this Gi values of one stage be different from the other stage in an overall effort of either increasing the power beyond this P in bar, which is what at the transmitter side would be, or you can reduce the power. Of course, you would not normally reduce the power. So, the design criteria at this stage seems to be that you choose this product I equal to 1 to n Gi in such a way that this term, okay, overall will be either greater than or equal to 1. You normally choose the option of being equal to 1, which means that your product I equal to 1 to n Gi is equal to 1 by e to the power minus n alpha LA, but 1 by exponential of minus x is nothing but exponential of x. So, you just pull this up to the numerator side, you get e to the power alpha n LA. Now, there are factors which are, there are n factors here, right. So, you actually have this factor G1, G2 all the way up to Gn. This should be equal to e to the power alpha n LA. One simple way of doing this or satisfying this constraint is to simply make all the amplifier gains equal to the same value, which is equal to e to the power alpha into LA, correct. If I do this, then the product of n such terms, product of n e to the power alpha LA terms is obviously going to be equal to e power alpha n into LA, correct. So, if this is equal to that, then you have the loss factor, total loss factor as e power minus alpha n into LA, whereas the total gain factor also being exactly equal to e power alpha n LA with a plus sign, of course, in the exponential argument. The product of these two will be equal to 1, correct, and the received power will be then equal to the transmit power, which is equal to the mean power that you have launched. So, this power is called as the launch power, and launch power is very important because you frequently in the literature find the performance of the systems either by giving the quality factor Q, which we have defined in the earlier classes, or by giving the bit error rate, which again we have defined in the earlier modules, and then looking at what happens to this Q factor or the BER curves as a function of P in. Considering this as a function of the BER, this is what you normally get. Okay. So, there is a certain optimum launch power for which the BER is small. Of course, in terms of the Q factor, this would be the opposite situation. So, there is a certain value at which the Q factor is maximum, okay, which corresponds to the optimum launch power, while the BER is at the minimum. Okay. So, this is for the Q factor. Interestingly, optical communication links kind of a very non-intuitive way of behaving with respect to Q and behaving with respect to the launch power, because as the launch power increases, you would actually think that, well, I am increasing the input optical power, which means that my signal to noise ratio might be very high. Why to stop at say 1 milliwatt of the input launch power or the 1 milliwatt of the launch power? Why not I make it into 1 watt? When you do that, interestingly, as you start increasing the launch power as a function of, increasing the launch power, okay, beyond the optimum launch power, what you see is that this curve actually starts to raise. The BER starts to raise again and the quality factor starts to drop. This fact, which is not normally seen in a typical communication system, in a non-optical communication system, is called the nonlinear regime, and this happens because as you start increasing the launch power, so this is the launch power that we have, as you start increasing the launch power, various nonlinearities will take over, which will then introduce an additional noise, which will then bring down the Q factor or increase the BER. Okay. So, the optimum launch power is the point where a linear regime, which is this fellow. Okay. So, this is sometimes called as quasi-linear as well. It is not exactly linear, but for all practical purposes it is linear. So, where this quasi-linear term meets the nonlinear regime, this is where you get the optimum launch power. Okay. We will not be able to look at much of this regime in this course, but do not worry, you can actually take up additional courses on optical communications if you are really interested as to why the Q factor or the BER actually behaves in a very different manner. Coming back to our problem, we have seen that the received power has been made equal to the launch power P in, correct. So, this is what we have done. We have done this by choosing the factor Gi into Hi is equal to 1 for all values of I from 1, 2, 3 all the way up to n, wherein the gain of each amplifier is equal to 1 by loss factor Hi. Okay. So, this is something that we have done with respect to the signal. If this is all that we had, our life would have been so easy. Unfortunately, what we have is just one part of the solution. We have not looked at what happens to the amplified spontaneous emission. That is what we want to look at. Go back to the circuit that we had, or go back to the system that we had. You have a fiber. Well, the fiber is not introducing any amplified spontaneous emission, so do not need to worry about that. The loss factor associated with the first fiber span is H1. So, this is my transmitter, okay. And at this point I put in a gain of the first amplifier, right. So, this is the gain of G. Now, you recall that we had looked at the noise sparse spectral density, correct, for a single polarization or for a dual polarization. This noise spectral density for a single polarization was given by NSP H nu of course being the mean optical frequency or the carrier optical frequency in our case, times G minus 1, correct. NSP H nu G minus 1, this was the power spectral density. If you multiply this one by the optical bandwidth B op, you are going to get the total noise component, right, or the noise power or the noise variance, right. So, this is what you would have obtained over here for a single amplifier. For a dual polarization, instead of 1 NSP you get a 2 times NSP because there are 2 polarization modes, but the power spectral density at this point is still given by 2 NSP H nu into G minus 1. Okay. Now, this power spectral density, okay, in addition to the signal, the noise power actually would see the same thing as the next stages. The noise is also seeing H2, G2, H3, G3. The first stage noise is actually seeing H2, G2 and so on, and eventually it will come to the optical band pass filter at which it gets limited. So, the spectral density and the noise power of the first amplifier grows as the length of the link grows. Why would it grow? Well, as far as the amplifier is concerned, whether the photons are coming because of the signal or whether the photons are coming because of the amplified spontaneous emission noise, they are exactly the same. They both are equal to each other as far as the amplifier is concerned. However, because of our problem they would not be equivalent, because for me signal is not the same as the noise, but an amplifier does not really care, and the fiber also simply does not care. It will start attenuating any optical power once the optical power is launched into the fiber. So, based on this fact that both amplifiers as well as the fiber sees noise as well as signal with the same way, the noise power of the first stage, so let us call this as PASC1, noise power because of the first amplifier, and let us assume for now just that we are working with single polarization, because for dual polarization you can always add another factor of 2, right. So, this would be equal to NSP H nu G1 minus 1, right. This is the noise power that is coming off because of the first one multiplied by the optical band pass filter. This then has to go through the stages H2, G2 all the way up to Hn, Gn. This is the noise power that you are going to get. What about the noise power added by the second amplifier? Well, the second amplifier also has the same spectral density. This would be given by G2 minus 1 B opt, the optical band pass filter, but it does not see H2, right, because H2 is now previous. So, this one is H1 G1. This G1 sees H2 and G2, whereas the second amplifier with a gain G2 would only see H3 and G3. For this H2 has already gone back. So, this would be H3 G3 all the way up to Hn Gn. So, if you continue all this and recognize that you are at some point on the nth amplifier stage, the power spectral density is still the same. The gain of the nth stage amplifier is G small n. The optical band pass filter is assumed to be ideal and has the same band value for everything, and this portion, this whatever the remaining factor that it sees, can be rewritten as j equal to n plus 1 to capital N H j g j. Okay. I hope this shorthand notation is now familiar. If not, you just go back to the beginning of the module and you will see what this term is. But you might question, well, we have already seen that H2 G2 must be equal to 1, Hn G1 must be equal to 1 and so on, right, and you are right, these factors are all equal to 1. But these by themselves are not the total ASC noise components, right. The total ASC noise is obtained by adding up all these elements, and you basically add up the nth stage amplifier noise, okay, n equal to 1 to capital N. There are n amplifiers and you simply sum all the n ASC noise components, and when you do that, because these factors are all going to be equal to 1, so this factor is 1, this factor is 1, in fact this factor is also equal to 1, then what is actually happening? Well, this is one factor plus this one and there are n such factors, right. So, what you get is NSP n H nu G minus 1, because all the gains are also the same, right, for each stage the gains are also the same, times the optical band pass filter. So, if you see this expression, you can think of this as the ASC power spectral density of a single polarization mode and an equivalent version of that multiplied by the optical band pass filter, where for a cascaded stage of n amplifiers, the equivalent ASC noise, okay, is given by n times the noise for the or noise spectral density for each amplifier, okay, having the same gain. Of course, it is very important for me to stress again that all the gains are the same, okay, all GIs are same and they are equal to just a factor of G, okay. There is one smaller thing that is associated with this one, okay. If you look at the ASC power, we will not prove this one, but you can see this one later. If you look at the ASC power and then you see this one as a function of the amplifier spacing LA, it turns out that as the amplifier spacing increases, remember as LA increases, e to the power minus alpha A decrease, which implies that e to the power alpha LA must increase, which means that the gain of the amplifier has to be increased. Obviously, if the loss is increasing, the gain has to increase in order to compensate for the losses. But what happens to the overall AAC noise power is that it actually starts to grow exponentially. Okay. So, as the amplifier spacing increases, the AAC noise power also, the total AAC noise power also starts to increase. Associated with this cascaded stage or in general any stage is the quantity optical signal to noise ratio. This is exactly like a signal to noise ratio, except that this is talked in terms of the optical signals. So, you have a certain mean power P in that you have received. Okay. So, this is especially at the receiver side that we talk about. So, the received power is P in bar. Why should it be P in bar? Remember, we have chosen H and G such that this is equal to 1, and therefore, all the amplifiers are going to compensate exactly for the losses, and the received optical power will be equal to the launch optical power P in bar divided by what is the total noise variance that you have for a dual polarization if you were to look at. So, this is OSNR for the dual polarization. Each amplifier has a power spectral density of 2 NSP h nu into G minus 1 in the bandwidth of B opt, okay, times N. This would be the optical signal to noise ratio. But what should I choose as B opt? There is actually no specific value. The kind of agreed upon value is that this should roughly be 12.5 gigahertz, which corresponds to roughly about 0.1 nanometers. Okay. So, this is the reference bandwidth that you choose, and within this reference bandwidth, whatever the signal power to the noise variance that you get is called as the optical signal to noise ratio. So, we have looked at what happens to the AC. We have looked at an optical communication system with what happens when you have multiple noise sources. What you can see here is that the noise spectral density actually starts growing linearly with respect to N. If you were to actually consider just this receiver side after a cascade of amplifier stages, if you just put a photodiode and then detect the signal, you will see that the Q factor actually depends on the square root of this N, so inverse square root of N. As the number of stages N increases, the launch power also must be increased. There is an additional side effect that happens over here, and this side effect that happens is because if you look at the saturation power, that is the output, what is the maximum output power that the amplifier can provide with a certain input power, the second stage saturation power must be slightly higher than the first stage, the third stage must be slightly higher than the second one, and so on. Okay. So, why should it be higher? Because the first stage provides the input signal plus it adds a little bit of a noise. Therefore, the total power that is going into the second amplifier has slightly increased, right. Therefore, in order to deal with that, the saturation output power has to slightly increase, and this actually happens all the way up to the end. Therefore, this is not very advisable to start reducing the number of increasing number of amplifiers N by reducing the amplifier spacing. So, there is a trade off over here, reduce LA, you reduce the AC power, but at the same time you are going to increase N, which means that the OSNR starts to dip. We are going to look at what would be the coherent receiver, look at the amplifier with the direct detection receiver, and what would the AAC noise do in the next module. Thank you very much.